Good morning, everyone. Welcome to the 15th Open Seminar in Frontier of Nuclear Physics. This seminar series is organized by the Institute of Modern Physics, the K Laboratory of Nuclear Physics and Ion Beam Application, Fudan University, and the Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. Is also sponsored by the Program of Introducing Terms of Disciplines to Universities, the Journal of Nuclear Science and Techniques, and it's live streamed on the co-share.com. And today we are very pleased to have Professor Wei Li from Rice University to give us a talk on the ultimate quark-gluon droplet at the smallest scales. Professor Li received his PhD in experimental particle and nuclear physics at MIT in 2009. Following a postdoc at MIT, work on the first relativistic heavy ion physics program at LHC. He joined Rice faculty in 2020. Professor Li's interest focused on the understanding emerging behaviors in strong nuclear force under extreme conditions. He has been a leader of the CMS heavy ion program since its inception, serving as the co-convener of the group and also project director of the time flight upgrades. His group led a surprising discovery of the Quark-Gluon Plasma in proton-proton and proton-nucleus collisions. He received an early career award from the US Department of Energy and the Sorin Research Fellowship, and a presidential early career award for science and engineers from the White House. Okay, now let's welcome Professor Li, please. Yeah.
Okay, so can you hear me okay?
Yeah, sure, perfect, please.
Yeah, okay. Yeah, so thank you. Yeah, so thank you, Jie, for the kind introduction, and also it's my pleasure to have the opportunity to discuss and exchange ideas with many of you on some recent development from my group at Rice. Yeah, so today I want to talk about the pursuit of the ultimate quark-gluon droplet at the smallest scales. This is a very active area of research in the past many years, even a couple of decades, with lots of surprises and puzzles, and still a lot of open questions we are trying to answer as of today. So I will first have a quick overview of the lessons we have learned in the past, and then I want to discuss a new concept that I and my colleagues have developed in recent years to push the limit of the so-called quark-gluon liquid droplet to the smallest scale. And we also have some recent experimental results where we see some intriguing observations that I want to share with you and hopefully trigger some discussions and interest. Okay, so to begin, so when we look up in the sky and think about our universe, and what has been really amazing is that how much we can actually almost understand everything with involving only 4 types of fundamental forces interactions, and involving only a handful of fundamental particles. And Higgs is the last one that, as we know, has been discovered in 2012 at CERN. And in the meantime, there are also a lot we don't understand. There are lots of very profound puzzles, and there are puzzles involving the type of energy and matters we can't directly observe, but we know they exist through indirect evidence. And there are also puzzles that involving the matter that we do observe, but we are still trying to understand why they behave the way they behave. So here, my interest, my favorite type of force is a strong force, and it is a force that involves the interactions of quarks and gluons. And the simple reason that I like strong force is simply because that it is the most complicated one among the four. It's the least understood one. So if you follow the golden lessons by Steve Weinberg, so we should go for the math because that's where the action is. There are still a lot we don't understand about the strong force, and it has a very rich physics, in particular at short distance scale, where the process involved large momentum transfer, and the strong force becomes simple, becomes weak, and it behaves like a Coulomb force. It's a phenomenon known as the asymptotic freedom, discovered by these three gentlemen who got Nobel Prize in 2004. However, as we go to the longer distance scale or process involving a small momentum transfer, then the strong force becomes complicated, becomes stronger, and fundamentally it is because of this type of couplings, the self-couplings among gluons that becomes more and more important, which leads to the phenomena such as a confinement that so we can never separate the quark from a antiquark, because as you try to pull them away from each other, the strong force becomes stronger and stronger. So there has been great successes of in understanding the strong force in the framework of the quantum chromodynamics QCD. For example, in using especially using the perturbative theory with the factorization theorem, one can very precisely predict the production of hard process in the hadron collisions, such as the jets at LHC. And even in the non-perturbative regime, using the lattice QCD calculation, one can also describe very nicely the spectrum, the mass spectrum of a variety of hadrons. On the other hand, there are also great challenges and limitations of our understanding of QCD, in particular for processes involving the dynamical properties, or the real-time properties of the QCD system, non-perturbative QCD system. For example, we still can't compute from first principle the parton evolution and fragmentation in the vacuum. So it's a complex system, so highly non-perturbative. We also can't compute the parton distribution function. We can't directly calculate how the most of the hadron mass is generated, and this is one of the biggest questions that, for example, the future electron-ion collider at Brookhaven will try to address. Yeah, so these type of systems, and the common feature for this system is they are highly complex, involves many body quarks and gluons. So question is how to look for simplicity out of this complex system. So can we find emergent phenomena with can we look for the orders out of these very sophisticated systems? So in ultra-relativistic nuclear collisions, this is an area that many of us have been working on. And so we took a maximalist approach where we use the biggest nucleus we can accelerate and try to collide them with each other to create the biggest mass as we can. And the expectation is that we'll create a extremely high energy density where a new state of matter called the Quark-Gluon Plasma will be formed. And it has deconfined degree of freedom of quarks and gluons over long distance, and and where the partons will interact and evolve non-perturbatively after it is formed. It has extremely high temperature, and it's also believed that in our early universe, our universe is in a state of hot and dense deconfined and Quark-Gluon Plasma. So here the key is that we need to create a very large system using large ions, so that there will be sufficient scatterings or rescatterings of partons to create a thermalized system to reach the equilibrium. And this is not traditionally, this was conceived to be not possible using proton-proton collisions because they are point-like, they are too small for any partonic rescattering to happen. So today, the Large Hadron Collider at CERN is the energy frontier of nuclear and particle physics, and this is where I study the hadron collisions and also high-energy nuclear collisions right now, and many of you as well, and also many of you also currently work at the RIC at Brookhaven. It's a collider as a with a lower collision energy. So at LHC, there are 4 experiments. So Alice was originally the experiment dedicated to the heavy ion physics, but as of now, all the 4 experiments are participating in the heavy ion program and producing highly competitive results. So I work on CMS. CMS is, without going into details, is basically a general purpose particle physics detector with large acceptance coverage, very high resolution, and it is about 15 meters in diameter in terms of the size. So in case that you may be wondering why we call it the compact muon solenoid, although it's so big, if you look at the amount of steels that you use in building CMS, so that's about two Eiffel Towers. So CMS has about 3,000 collaborators, and about 30% are interested in the heavy ion physics, and we'll definitely welcome more collaborators to join. So this is a display of a central light events registered by the CMS experiment, where there are up to 20,000 particles produced in a single collision. And so the main strength of the CMS is the large acceptance coverage. As you can see, the calorimeter has a coverage up to 10 units in rapidity, where the tracker can cover 5 units in pseudo rapidity. And in a very far forward region, we also have the 0-degree calorimeter for detecting the forward-going neutrons. CMS also has a very high rate of the online trigger capability and data acquisition systems. So we can record a lot of events. So the most successful story of the heavy ion collisions is the discovery of a perfect, so-called perfect liquid or perfect fluid. To explain what it means, basically, if you think about the initial state of the heavy ion collision has a almond-shaped initial geometry, and subsequently, as I mentioned earlier, there will be strong partonic rescatterings such that the strong pressure gradient will be developed, and under this pressure-driven expansion, this initial state symmetry will then be transformed into the final state azimuthal anisotropy in the momentum space. So as illustrated in this picture, as taken for the not for the heavy Quark-Gluon plasma, but for the ultra cold atom system, where you prepare it initially in this cigar shape, and then you release it, and then the expansion rate along the short axis of this cigar shape or the elliptic shape system is faster than the expansion rate along the long axis. So in the end, you develop this azimuth anisotropy, where we can clearly see that in our detectors, event by event, directly by eye, where this is the energy registered in the calorimeter of the CMS experiment. And we are interested in, so this is called elliptic flow, and we are interested in the magnitude of this anisotropy and try to infer the properties of this fluid-like system. So there are many approaches to study the elliptic flow, and I will, because I will show a lot of the two-party correlations results later. Let me spend a moment to explain the approach that I'm my favorite approach to study elliptic flows, which is using two-party correlation. So imagine you have, in one event, you produce lots of particles. So we sample the momentum vector of two particles at a time, and then we look at the angular difference between the two particles in the delta eta and delta phi. Then we'll build a two-dimensional distribution of the pair, all the pairs that we can create, and create a distribution as a function of delta eta and delta phi. So if we do this, for a light collisions, and this is the typical distribution we will get, where if you ignore this peak here at delta eta, delta phi close to 0, you will see a quite simple structure that is extends over the long range in delta eta, and in delta phi there's this cosine 2 delta phi like distribution, and this is what we call elliptic flow. It has the cosine 2 phi shape, and the magnitude of this cosine 2 phi, which we call V2. So here is V2 squared because we call it two particles, is the quantity we are interested in, the magnitude of V2. So to show you another example of the two-party correlation, now this time for a collision that is almost head-on, for such a collision, you see that this elliptic initial shape becomes much smaller because the collision is almost head-on. It's almost spherical, but there are fluctuations around this near the spherical shape, which also give you initial geometry anisotropy, which will then be transformed into the final state anisotropy. So again, in such a collisions, you still see this long-range structure, but now in delta phi is not simply a cosine 2 delta phi, but there is more complicated, more structures which we can do a Fourier decomposition and extract not only V2, but also the higher order terms, V3 and V4 and so on. This corresponds to this higher order come from the higher order initial deformation that's again transform into final state through these strong partonic rescatterings. And this long-range structure, especially at around delta phi equals 0, this is the particle correlation alignment in phi, which we usually call near side ridge, and this is considered a hallmark signature for the onset of the QCD collectivity or the Quark-Gluon Plasma fluid. For example, to convince you to contrast the same two-particle correlation we observe in the proton-proton collisions, for the minimum bias events, you can clearly see that the main difference between two is that there's no near side ridge in PP. Then the structure in PT is relatively easy to understand because this peak comes from the mini jet production of the particles. They are produced very close in eta and phi, and this broad away side around delta phi equals to pi come from the momentum conservation process for the back-to-back process. So this seems to consistent with expectation that in PP we don't the system is too small to form a Quark-Gluon plasma. So the study of the collective flow has becomes a very kind of a standard paradigm in the heavy ion collisions with more details and much higher precisions. So, for example, this is a result that from CMS that shows the extracted V2, the elliptic flow, and also the higher order flow V3, 4, 5, 6, all the way to 7th order compared to the hydrodynamic calculations, where you can see that through this comparison, we can already get a first order constraint of the shear viscosity to the entropy density ratio for the QGP to be within around 0.1 to 0.2, and this is a very small number. And more recently, there's Bayesian, more systematic Bayesian analysis of the flow data, which puts an even stronger constraint on the viscosity of the QGP, including its temperature dependence, where you can see that compares to the like the water and liquid helium, the ETOS of QGP is order of magnitude smaller and is very close to this theoretical bound from the ADS-CFT calculation. So this is the limit, kind of the limit, lower limit determined by the quantum fluctuations. You can't have exactly zero viscosity or zero mean free path. Is the minimum value allowed by that quantum fluctuations is around 0.08. So therefore, that's how we conclude that QGP is a strongly coupled, nearly perfect liquid because it's as perfect as it can be. It is allowed by the by quantum fluctuations, and it is extremely efficient in converting this initial anisotropy to the final state. So the whole framework has been extremely successful and well established until around 2010. The small systems now strikes back. Earlier I mentioned the small system, the PP collisions is kind of boring because it doesn't produce a QGP. However, a surprise in 2010 is at LHC, when we look at the PP collisions where occasionally in a single collision, you can produce also a large number of particles, like more than 100 particles. So those kind of rare high multiplicity PP collisions, in the two particle correlations, we have also observed a hint of the near side ridge. It is small, but it's quite significant. So this is it's a small system. It's still PP, but we try to make it denser by looking at its high multiplicity events, and it resembles some similarity to the elliptic flow that we see in these light collisions. So if this is not yet convincing, then a couple of years later, LHC has collided the proton-light collisions, where in the high multiplicity proton-light events, you can clearly see that the signature of elliptic flow, and it's obvious that there is a strong similarity between the P-light and light, and also proton-proton. So at this point, we can really ask whether we have seen the universal collective signature and possibly a QGP across all the systems, not only in the large heavy ion collisions, but all the way to the smallest proton-proton collisions. Of course, I should mention that at the time there are lots of alternative interpretations, such as the gluon saturation model in the framework of color gas condensate. There are also parton escape mechanisms. Well, we're still discussing those as of today, in fact. And on the experimental side, I'll use this slide. I try to, this is the condensed summary of the many, several work that has been done in the past many years. On the experimental side, we have gathered more data and look at more observables. For example, we studied how the elliptic flow in different systems depends on the particle species. From the light hadron to the heavier hadron, we can see a kind of the ordering of the V2 based on their mass, and also the famous quark number scaling that's first observed in the heavy ion collisions. They're all very similar for the three systems. Later, we have also studied the multi-particle correlations going beyond 2 particles, study 4 particle, 6 particle, and 8 particle correlations. And what we have observed is that no matter how many particles you correlate at a time, the V2 you extract is always similar, which directly shows that what we are seeing is indeed a collective effect, so involving all the particles produced, not only among 2 particles. Again, you can't see obvious difference between at the qualitative level between the proton-proton, P-LED, and lead-lead. So it looks like this what I call QGP signatures with some quotation mark is indeed universal across 3 systems. So this picture of the strong partonic rescattering with some initial geometry not only applies to the A collisions, it can also be applied to all the way to the PP collisions with a scale of on the order of Fermi. And so yeah, I put a quotation mark on here for QGP. What I mean is that we may not a lot of signature we have seen may not require a thermalized system. If that's a requirement for the definition of QGP, we're not saying that there is a thermalized medium also formed in all the way in the proton-proton collisions. So that's something still being debated. Okay, so let me to summarize a bit here the lessons we've learned. So it is evident that the QCD collectivity or the QGP signatures are not limited to only the large systems. They also extend to the smallest systems we have studied. So the question that one always asks is how small is too small? So how small we can make the QGP-like system, the QGP droplet. So and what conditions would partonic collectivity really emerge? So we started with this large system. The system size is a lot bigger than the typical mean-free path of the scatterings. Then we go to the minimized collisions. The collectivity seems to disappear because your system size is probably becomes comparable to the interaction mean-free path, which is not unexpected. But then when we try to make the small system denser to reduce the interaction mean-free path, and the collective effects emerge again. So it looks like is a interplay between the size of system and the density of the system, or the mean-free path of system, and certainly is certainly not only determined by the size alone, right? Also, is the partonic collectivity observed at these very small scales really unexpected, or is actually not so surprising? It's maybe a natural consequence of QCD in its non-perturbative regime. Because when we talk about the QED force, right, the QED force is weak at the two-body level. Therefore, when we make a strongly correlated electron system, that is indeed a surprise, right? However, the QCD is intrinsically strong. So maybe it's not so surprising that if you make a many-body QCD system, it's always strongly coupled, because the force is fundamentally strong. And during the process, we also thought about there are other type of non-perturbative dynamical systems in QCD that we don't have a very good understanding or good tool to describe. For example, one example is the parton fragmentation in vacuum. We only have phenomenology models. So can hydrodynamic be an effective tool to describe those type of processes. Yeah, so here we came up with a somewhat proactive postulate in our pursuit to the ultimate smallest limit, how small you can make a system. So can we make a QGP-like system initiated by a single parton? Can we start with a single parton in the vacuum, right? So you can't make a system smaller than a single parton. So that is the ultimate smallest limit. So how do we do that? So I'll try to explain this in the rest of my talk. There was, some of you may know that there has been a long-standing puzzle observed in the E+ and minus collisions, that when you look at the particle multiplicity production, different type particles, and they can be described very nicely to good approximation by a thermodynamic approach. And this was first pointed out by Francesca Beccattini a long time ago, 2 or 3 decades ago already. And of course, it's commonly, it is believed that the E+ and minus is elementary collisions, and you don't expect any kind of multiple partonic risk scatterings, right? So usually we don't allow description of the multiple partonic risk scatterings. So we don't expect any kind of thermal-like state to be developed in the E+ and minus collisions. So what's the origin of this thermal behavior? Of course, I should point out that this is the common perception, which is never proven experimentally. So therefore, it doesn't have to be right. There are also proposals that maybe the entanglement entropy can generate so-called quantum thermalization without these kind of classical interactions, risk scattering, which can also give you a thermal-like final state. And there are also, I believe, many people just think that this is just a coincidence somehow, that there's a similarity of the E+ and minus to the heavy ion collisions. But in any case, and at the same time, not at the same time, in recent couple of years, there has been an effort to try to actually look for the evidence for the collective effects of the flow directly in this small, even smaller system like E+ and minus. These are 2 particle correlations in E+ and minus, and then in electron-proton from Zeus, in the photon-proton using the UPC P-like collisions, CMS, and also in the gamma-like events. So these systems, in some sense, they are even smaller than proton-proton, even point-like. In this system, so far there's no unambiguous observation of collectivity yet. There might be some indication, but it's far from clear. The reason could be that they're just too small and dilute, that you can't really form any, let's say, the QGP-like state. But then the question comes back to the E+ and minus. How do we understand the E+, this thermal behavior in E+ and minus? It could also be that the multiplicity range is too limited. Yeah, go ahead.
I just want to emphasize this is a real real photon, or near real photon proton effects, right? Not what.
These 2 are real photon. These through the ultra peripheral, the ultra peripheral P-like.
Real photon.
So this one is more like the virtual photon proton in EP collisions. Yeah. So yeah, I want to point out in all these searches, the multiplicity are quite limited. You see that it's hard to get to very high multiplicity. You can get to 20, 30, 40, but it's way below a couple of hundred particles where we see the clear near side ridge collectivity in proton-proton collisions. So maybe we just have to go to higher, because at low multiplicity we're overwhelmed by the other effects, the non-flow effects, other field body correlations. Yeah, so when looking at these E plus E minus events, if you think about E plus E minus, it's like a production of a quark and antiquark pair, and at high energy, it's just like a digit, right, back-to-back digit. And then if you think about in proton-proton collisions, we produce digests at all the time. We produce lots of them. It's not the same process. Sometimes it's of course gluon, not just a QQ bar. But in the proton-proton collisions, especially at LHC, this is a event display we made with PCR in this paper I wrote with my colleagues. In this proton-proton, we can find a lot of much higher multiplicity jets than in E plus E minus collisions with very high energy. So this one, for example, has nearly a TeV energy and fragment into over 100 charged particles. So the question is whether we can see any evidence of partonic ray scatterings in those kind of jets. So it's also it's a localized high density region, right? So this what triggered our interest to look for the evidence of the QGP-like effect in this type of jets. To elaborate on what we have in mind, and I need to quickly review the properties of the vacuum, because the vacuum is not empty. For example, for the QED vacuum, it's filled with virtual electric charge pairs. And now you think about what happens if we put a free electric charge in the QED vacuum. And there will be no new charge produced, right? What will happen is will create a effect of the vacuum polarization and the screening effect. And unless that you make your electric field extremely strong and a certain limit as predicted by Schringer, there will be a so-called Schringer effect that the free charges will start popping out of the vacuum in the case of extremely external field. So to have this analogy in mind, let's now go to the QCD vacuum. So QCD vacuum similarly is filled by now the virtual color charges. It's known as the chiral condensates, which brings the chiral symmetry. There are quark condensates. There are also gluon condensates. Now imagine what happens if we put a free color charge, one free color charge in the QCD vacuum. This is of course only a hypothetical scenario, but if you just bear with me to make the point, in this case the energy of this color charge will be infinity, right? So you have extremely strong color field, which will immediately pull the vacuum charges, the chiral in the chiral condensate state out of the vacuum. So immediately this initial parton will be surrounded by this quark and gluons excited out of the vacuum, and they could interact with each other, and then become a system that expands like a Quark-Gluon Plasma with the center of the initial partons. Expands like a QGP maybe. But again, this is a hypothetical scenario. To be more realistic, let's say let's think about now I have a parton that's moving, or you go to a frame where the parton is moving in the vacuum, and so this single parton will excite a lot of secondary quark and gluons out of the vacuum, and if the density is high enough, they could ray scatter, they could expand around this axis and maybe behave like a Quark-Gluon Plasma. So this is a scenario we could actually emulate experimentally using the jets. Now we can take E plus, E minus, or proton-proton or EP collision, and then in the hard process, let's say proton-proton, we produce a digest, the two jets. If we look at just one jet, so we will rotate the axis of the frame where such that the direction of this hard scattered parton will be pointing along the z-axis. We will define that as a new axis frame. So therefore, in this new frame, which we call jet frame, the jet direction will correspond to the rapidity infinity, which we call now eta star infinity. And direction perpendicular to the jet axis is mid rapidity, eta star equals 0. So in this frame, so this is like you shoot a parton into the vacuum. You shoot a parton into the vacuum, and then it will fragment. The process of fragmentation can be thought as a process when the parton start to excite the vacuum condensates to the excited states, and they may again, when the density is high, then they may re-scatter, they may expand just like a Quark-Gluon plasma, and at some point hadronize into the final state partons we observe. So usually when we study jets, we define a cone size, right? So a jet with a 0.8, a side cone 0.8 corresponds to my eta star about 0.86. So this is the boundary of the jet. So in this process, it involves initially the perturbative process in the hard scattering, and later the fragmentation is a non-perturbative process. Especially this soft, so-called soft radiation, and maybe if the coupling is strong, maybe they can also reach the hydrodynamic limit. So yeah, our question is whether we can observe a near-side ridge in this type of high multiplicity jets using this new frame. Okay, now go to the experimental data now. This is an event that we recorded in CMS using the nominal PP data. The proton-proton data is not heavy ion data. We use all the proton-proton data that's recorded from the LHC run 2 by CMS so far. And this is a digest events with at least one jet about 550 GeV in PT. And we use a jet cone size of 0.8 NDKT jet finding algorithm. So you can see here, this jet is a normal jet which fragment into 10 or 20 charged particles with very high energy registered in the calorimeter. And in the way side is an unusual jet, it's a rare jet, where this jet has produced more than 100 charged particles just in one jet. This is a distribution of the multiplicity inside a jet, where we can see this steeply falling. And if we select on above the number of charge multiplicity inside jet about 90, we have something like 2,500 jets out of about 100 million jets we have analyzed. And so some details here that there in these PP events, there are pileups that we have to mitigate. And also we only analyze particles clustered into a jet. So for the particles outside jet cone, outside the single jet cone, they do not enter the analysis. Part of the reason is that it's hard to distinguish them from the pileup events. Yeah, so therefore, back to this cartoon, we only analyze particles clustered into the jet cone. And with those particles in this new jet frame, the first thing we can look at is the charged particle rapidity density. This blue distribution is for this high multiplicity jets, where you can see that in terms of the DND eta star, it can reach already close to 70. 70 is comparable to already to the particle density in producing these peripheral A collisions. So in terms of particle density, is fairly high in these high multiplicity jets. Okay, so next we look at two particle correlations in this jet frame. We first look at this normal jets with average charge around 26. And you can see that in the jet frame, we don't see the near side ridge. We don't see a near side ridge, but you can also see the structure, the correlation structure we've seen is very similar to what we see in the minimum bias collisions with respect to the beam axis. We see the peak just from the field body correlations, the mini jet or mini subjets in this case, because we look at everything inside jet cone. There's a away side from the back-to-back correlation momentum conservation process. This also holds when you look at the particle fragmentation inside jet cone. So the dynamic of particle production actually is not so different when you look at the particle inside jet or look at the minimum bias collision with respect to the beam axis. And you can even think about the minimum bias PP collisions as kind of after they excite each other, right? The excited proton becomes three jets going down the beam line, and then they fragment, and the three jets could interact with each other. But fundamentally, it may not be the particle production mechanism may not be so different by the particle production from a single jet. And that's kicked into the central region of the lab frame. Okay, so then what happens if you look at the high multiplicity jets? Now we look at the high multiplicity jets that produce over 100 charged particles. Now you see that there's something that's emerging here at the small delta phi, and over the long range delta eta, we see some indication of the near side ridge in this high multiplicity jets. Right? You can see it's of course not so may not be so significant yet because we are limited. We have used all the data available, but it's clearly there's something there that looks intriguing. So to compare to this, what predicted by the Monte Carlo event generators, we have compared to the PCI-8 and also Shepard, where the PCI-8 is all about how you model the parton fragmentation. So for PCI-8, use the string hybridization model, whereas the Shepard use a different approach to the cluster hybridization model. So we want to compare two different mechanisms. So for normal jets, you see that there's no near side ridge in all cases for data and two Monte Carlo models. Whereas if we move to the high multiplicity jets, as I shown earlier, that we start to see some indication of the near side ridge emerging in these high multiplicity jets, which we still don't see in any of the two Monte Carlo models that we looked at. To look in more detail, now we focus on only in one dimension in delta phi, make a projection from the large delta eta region so that we exclude this jet peak. And from the low multiplicity jets to the high multiplicity jet, you can see from the near side from delta phi, small delta phi, it goes from a minimum and starts to turn into a local maximum. In a way, that's very similar to what we have observed in the proton-proton collisions from low multiplicity to high multiplicity. This is the analysis with respect to the beam axis. And again, comparing to the Monte Carlo models, PCI-8 and Shepard, we don't see any near side enhancement either from low multiplicity or high multiplicity. So this seems to be a unique feature in the data. To be more quantitative, we can do the Fourier analysis to extract the anisotropy flow coefficients. So we perform a fit to the to the one-dimensional delta phi correlations and to extract the different terms of Fourier coefficients as a function of the jet charge multiplicity. And what we observe is that for the even order, so the odd order harmonics are negative, and the even order harmonics are positive. The magnitude tend to decrease as you go to high multiplicity, and this is there's actually a very good agreement between data and PCI-8 prediction for these harmonics, all the way to somewhere around n-charge 80, the n-charge in jet 80, where beyond 80, then we start to see some indication of the deviation, especially for V2, and even maybe a little bit for V3, for n-charge greater than 80, which may indicate the onset of some kind of new physics phenomena. So to zoom into V2 only, so here we extracted the single particle V2 by taking a square root of the two particle V2 coefficient. The small V2 is what we usually call elliptic flow. When we look at small V2 as a function of the in-jet multiplicity, you can see that clearly for the models, for PCI-8 and Sharper, they both monotonically decrease as you go to higher and higher multiplicity. And this is what you expect if the correlations are dominated by the short range and few body correlations. So you increase multiplicity, they start to get attenuated, that suppressed. In the data, this is also the decreasing trend is also the case in the data, but until around n-charge 80, we can see that the V2 starts to level off and then turn back up. Now, if you look at focusing on these last 4 points, and here I show you how this correlation structure evolved. For these last 4 points, from here you don't see any near side enhancement. To go to higher and higher multiplicity, and you start to see the near side starts to turn into some enhancement, and the highest multiplicity, the enhancement becomes more stronger. So we clearly see, even though we may not see a clear near side ridge, but there's clear observation of enhanced V2 or elliptic anisotropy as we go to higher and higher in-jet multiplicity, which may indicate possibly the onset of collectivity in these very high multiplicity jets. We also look at this in different intervals of the particle transverse momentum respect to the jet axis, which we call JT, from 0 to 3 GeV, 0.3 to 3 GeV, 0.5 to 3 GeV. So in all cases, we see qualitatively the same observation that the enhancement of V2 as we go to higher and higher in-jet multiplicity, and they are significantly at high multiplicity. The data significantly deviates from what's predicted by the Monte Carlo models, where in those Monte Carlo models there's no partonic rescattering effect implemented in the jet in modeling the jet fragmentation. So that may be a key missing piece. Yeah, so at this point, I hope that the evidence is compelling enough that we can start to ask, maybe we have formed some kind of QGP droplet-like state initiated by a single parton in the vacuum. And maybe this is a solution to the thermal puzzle in E plus E minus. E plus E minus, maybe there is rescattering effects involved, but you have to observe that only when you go to sufficiently high multiplicity through the particle correlation analysis. Now, one thing we have to think about to generate elliptic flow, we need a geometry, right? We need a scattering we also need initial geometry. So how to think about initial geometry of a parton? Because parton usually we think is a point, right? However, we also know that nothing can be exactly a point. So if parton also have some virtuality, therefore any fluctuation, any quantum fluctuation could give a parton some kind of initial size or even shape as a starting point to develop a final state as smooth anisotropy. One simple way to think about it, one simple picture is to think about maybe there's the early splitting of the parton into two prons, and then you can treat that like a two hotspots with ellipticity, and it's like a deuteron, and then subsequently, then these two hotspots will have to interact with each other as they propagate in order to generate any final state V2. But if they don't interact, then you don't get anything. This is something that there's no model actually considered, and yeah. So the question is, how do we model this initial space-time distribution of a single parton? This is far from clear, right? It's not like in the lead or proton we have some idea about the size of the shape of the initial stage. For single parton is more like a guess. Yeah, I should also, without going into details, I should also mention that there's a very interesting connection to the study of the jet substructure. And for example, we can study the correlation of the signal we observed to the jet splitting function to see whether there's any correlation. When enhancement of our signal, when we see a clear two-prong structure. And in some sense, what we are looking at is some kind of a substructure, but we are more focusing on the non-perturbative aspects of the jet substructure. There are many other heavy observables we plan to look at. For example, we can look at the strangeness enhancement that has been observed in the PP collisions. We look at the PCR. The PCR doesn't predict any strangeness enhancement inside the jet. We can do the multi-particle correlations to directly probe whether the signal we observe is a collective effect. One can also do the Bose-Einstein correlation, so that will provide some constraint on the size of the initial source, but it's not the Bose-Einstein correlation measures the size of the free result, but at least it give you some upper limit on the initial size. One can also discuss jet quenching in the vacuum. So in fact, in our picture, that there's no fundamental difference for parton losing energy in the vacuum versus the losing energy in the QGP medium. You lose energy by interacting with surrounding partons, but in one case you interact with the partons in the ground state, in the chiral condensate. In the other case, you interact with excited color charges. So in any case, basically our ambition next is to repeat the full heavy ion program in these high multiplicity shares. So this brings me to the end of my talk to give you an outlook at the LHC. This is where we are right now in 2023. So the data we have analyzed so far is only about 5% of the full LHC program planned. And by the end of run 3, the LHC will deliver about 15% of the full program. And then looking into the future with the high luminosity LHC that's starting around 2029. So eventually we expect to collect tens of thousands of these high multiplicity jets where we can do very detailed studies. This is just in PP collisions. I didn't mention so our rich program in heavy ions. So besides the higher luminosity, there will also be major upgrades of the detectors. For example, in the CMS, we will have even wider acceptance, coverage, finer granularity, even higher trigger and data acquisition rate. And we will have a detector that can provide the particle ID for the first time in CMS to flash some of the upgrades. And this is the tracker, the future of the CMS tracker that will cover up to pseudo rapidity equals to 4. And this is how the two-particle correlation will look like by the high luminosity LHC, where we can have the reach over even more extended region in delta eta. Right outside the tracker, we'll have a new timing layer, which will provide a excellent time resolution of 30 picosecond per particle, which will provide us the hadron PID capability for the first time in CMS, and will also make CMS the most complete detector for the heavy ion physics program. And this is also a program that I'm personally heavily involved in, and there are major contributions by the US heavy ion group in the NCAP of this timing detector. So this brings to my summary briefly. There has been tremendous progress made in discovering and understanding the QCD collectivity in small systems that was not originally expected. So this triggered the question, some of the very fundamental question, like how small is too small to make a QGP like liquid state? Is collectivity truly universal in QCD? And also, the other question I mentioned earlier, is it intrinsic in QCD? Do we always create a strongly coupled system? So we propose a new idea to push to the ultimate smallest limit to initiate the QGP droplet with a single parton fragment in the vacuum, and we have performed a experimental study of two-particle correlations in the high multiplicity jets in PP collisions in the jet frame that we defined, and we have observed a indication of the onset of collective signal in the very high multiplicity jets. And so we still have a very exciting and rich program ahead at the LHC, at the CMS, and I hope this will also excite some of you to join the program in the future. Thank you.
Okay, thanks, Wei, for the nice talk. So now the seminar is open for questions. Please open your mic if you want.
李伟，
文斌，
我新年，那个，
新年，
你这个 ，if I have a real quick look at this, this near side ridge, it looks like the ridge is not uniform in rapidity. Or have you checked, or it's just a visual effect? There's fluctuation.
You mean whether it's flat in rapidity?
Yeah.
We can't tell because the at this scale is pretty flat because the scale doesn't start from 0. You see, it's from with surpass 0. So this is within this range. It looks like the fluctuate a lot, but it's a zoom in effect. It's a zoom in effect, and certainly at the edge the fluctuation is bigger.
What is the edge? The edge is so. What is this is you define the rapidity sort of like along the jet direction, right?
Yeah, that's right.
So
the
rapidity range could be very large. I mean, so why do you stop 3 or?
It's not that one. I have a plot. Back. I'm trying to. Yeah. So that I show the rapidity distribution in this new frame. This is how it looks like. So the rapidity distribution cut off around the point 86. That's the boundary of the jet, and so the red point is the normal jets, the normal phase jets, which can extend to 5 or 6. So the high multi-phase jets actually narrower.
It's very narrow. The high multi-phase is very narrow. I mean, once you go to like 3, you're almost, like an order of magnitude away from the peak multiplicity.
Correct. So that's why our delta eta star range is somewhat limited, because the rapidity distribution is not like in heavy ions with a long plateau. In this case, it drops faster. It's also a known effect in the high multi jets tend to have big gluon jets with more soft radiations in the a large angle from the jet axis. So the higher multiplicity you go, then the distribution tend to become narrower.
Yeah. So there are really many variables in this case, and you use the jet cone size of 0.8, and the one question is what is the the so-called ridge you're looking at, where the particle come from? Is coming from the edge of the cone, or is the center of the cone? And this is also, you are looking at the dijet, and you're only looking at particle in the away side, right? On the fat jet, not the energetic jet.
We only look at one jet. So most of the time is a dijet. So most of the time there are.
So you only look at a single inclusive jet, not the dijet configuration.
Normally. Because when we select high multiplicity, we select high multiplicity on one jet. We can look at two jets later, but two jets, there are more variables, right? Because then you have to ask, do you select high multiplicity on both jets or high multiplicity only on one jet?
Yeah. Well, I mean, jet is they always come in pair. I mean, single jet means there's always the other jet on the other side, right?
Yeah.
So, and then this is why the color flow is very different than E plus minus. The jet in the PP interaction, the color flow is very different than plus minus. So I think that's the reason why the E plus minus is different than here.
So you mean color? But in which sense is different? You mean the kind of connection to the remnant proton?
Yeah.
Right. So that, but keep in mind this, we are looking at very high energy jets. So these are several hundred GeV parton.
They are still have kind of some kind of color connection.
Yeah, there's some, right? But if you go to a very high energy limit, the color connection to the remnant should become small, relatively speaking, but smaller and smaller.
Yeah. So I think there's two things you can do. One is look at the jet cone size. I mean, now you're looking at very large cone. I mean, what about like 0.4, 0.5?
Yeah.
And then furthermore, with regarding to color flow, you can also look at the gamma jets, because gamma jet, the flow is very different from the single jet, dijet.
Yeah, I think these are very good suggestions. So just to comment, we did look at we look at the largest cone possible, because this maximizes our delta eta star range. We did try to reduce to 0.7, 0.6. We see a similar enhancement of V2 at high multiplicity. And 0.4 becomes difficult because then our eta range becomes really so 0.4, the eta star will start around 1.6. It really cuts off very large portion of our phase space. So yeah, point 4, we don't have the statistics or coverage to claim one way or the other. But
Okay.
the gamma jets is a good idea, and we'll try to look next. So in the case of gamma jets, of course, most of jets are quark jets. Quark jets is a little is more difficult to get to the very high multiplicity compared to the gluon jets. So we may need more data to collect more data.
Yeah. Okay. Thank you.
Okay, next Wenbin.
Okay. Thanks for nice talk. Can you turn to page 19 or 18 just to show the collectivity in gamma lead? Yeah, I want to comment that seems next year this one. I mean, I want to comment seems Atlas has extracted the non-zero V2 and V3 in gamma lead collisions, and also compared to the PP and the PLED, right? So can we claim we observe the collectivity in gamma lead, the high multiplicity gamma lead collision?
Yeah, right. I say to hear what I said, non-unambiguous observation of collectivity yet in any of the system, and I would be convinced if the following happens, if the following are seen in gamma lead or any of the system, if we directly see the near side ridge, and if we see a V2 from multi-particle correlations, for me those are the unambiguous signatures. If you're extracting V2, all these systems you can extract the V2. And you, of course, the Atlas analysis has done a subtraction of the non-flow effect, and we will have to ask how model dependent that subtraction is. I'm not claiming that I'm not saying that the signals are not there, but yeah, so for me is not yet unambiguous. Especially compared to the level of understanding in PP and PLED, I think there's still some pieces missing.
Okay, thank you. Maybe can I have another question? When you talk about how to model the initial geometry of the collectivity inside the jet core, I still do not quite understand how to model that.
So, right, I don't know either. I'm just this is I hope this will this can trigger some interest, especially for series to think about it. What we do know is that to have a final state anisotropy, we do need some initial geometry. We need some fluctuation. Let's say if you apply hydrodynamics to a parton to a jet, you have to start with we need to start some geometry. So where can that come from? So one idea is that the parton, the earlier splitting of the parton tend to be harder, and so that can give you a two-prong. So one parton could immediately so once the one parton enters the vacuum, it could immediately becomes two prongs. The two prongs could be act as two hotspots. So this is a guess of the first guess is that you treat a parton as the two hotspots from early splitting, and these two hotspots then will evolve, and they can interact with each other. So if you run a hydro model, you can imagine that two hotspots will develop into some final state V2. Right.
Okay, so there is also some energy gradient. The central is highest and decreased.
The energy gradient. Well, each of them will expand individually, and then the shock of the two hotspots will collide, and then I think that along this direction, you get larger, you get more particles. So yeah, it's like a deuteron gold collision, right? In the deuteron gold, it's a two hotspot collide with the gold, and then the two hotspot will expand and collide with each other and develop some kind of ellipticity. So maybe we can apply the similar idea to a parton. But yeah, but as I said, it's or you think about any type of fluctuations, any type of fluctuation that can give you some anisotropy, and usually the second order tends to be the dominant one. One can start with just ellipticity.
Okay, thank you.
Okay, next, Professor Wang Qun, please.
Hi, Li Wei. Very nice talk. Thank you very much. My question is about what's the main reason for these high multiplicity events? Is it because of the multiple scattering? For example, in conventional QCD treatment, you just treat the parton creation, parton process as a once. Maybe there's do you know any theory can treat the multiple scattering? For example, at the same time, there are two pairs of the partons collide to produce these high multiplicity events.
Right.
What's the main reason for the high multiplicity events?
Yeah. Okay, this is a good question, but I want to first clarify that we are not looking at the high multiplicity events in the sense in the sense of high multiplicity of the PP that we studied before. So previously when we study high multiplicity PP, we look at the we look at number of particles produced from the whole event. Now this time we look at the high multiplicity jets. So we count the particles only within the jet cone, and we select high multiplicity only in the jet cone. We don't look at the rest of the phase space. So I think the question becomes previously I think the high multiplicity PP collisions or what we studied previously. I think the mechanism to produce them is the multiple. It's a lot of NPIs, a lot of multiple parton interaction initially that produce those events. Now this time is a single parton. It's a single parton producing more than 100 particles, charged particles. So this is a key difference. Then we can ask. Sorry, yeah, go ahead.
Yeah. So inside this jets, you observe this the long range. It seems that there's a collectivity.
That's correct, and it has to be, so the kinematics needs to be defined with respect to this new frame. So it's long range in this new frame in Eta star. It's not long range in the lab frame.
I see.
Because the lab frame, everything is in a small jet cone, but when we rotate it, when we redefine the jet axis at eta infinity, and so it becomes long range in that frame.
Yeah. Another question is, in PP collision, can you measure the impact parameter according to the multiplicity?
Not obviously.
In the central collision of PP, then there's a high multiplicity, and in the peripheral collision of PP, then you have a lower multiplicity. Can you do that?
We can measure high multiplicity, low multiplicity events. The question is whether it corresponds to the impact parameter of PP collisions or not, and that is not it's not an experimental question, right? Because we don't measure the impact parameter. Well, we know in AA collisions there is good evidence that the impact parameter and multiplicity have a strong correlations. But in PP or even in PLAD, this correlation becomes obscure. It's not so clear. In PP, you can make this connection.
Okay, thank you.
Okay, next, please, Professor Huang, please.
Yeah, wait, nice talk. I really enjoyed it. So could you go back to the comparison between the PCR and the data for the VM?
VM, yeah.
Yeah, okay, there. So, I mean, I noticed that, you talk about collectivity, but you also talk about possibly the Quark-Gluon Plasma or drop of matter. So do I understand correctly that you do differentiate? No, I mean, there are some collectivities that can due to multi-parton interactions or something that perhaps already in PCR as well, but we not necessarily will call those things as a Quark-Gluon plasma or as a drop of matter, as a bulk matter per se. So do I understand correctly? You differentiate that part. Okay, if that's the case, then if I've interpreted that comparison, I would say perhaps below say 80, multiplicity 80, that most collectivity could be produced by some kind of parton interactions, in the PCR kind of, I mean, at least in PCR. But then the question would be, what would be needed to unambiguous to say that above some 80, the deviation that really you do form a matter, bulk matter, that to be, because the way I see a bulk matter, I needed to have a way be able to describe the geometry, the shape of the matter. So in AA collisions, okay, I can see that the global geometry. Right? I can see the calculated eccentricity and the V2, and I see clear correlation between say V2 and the eccentricity, and I say that is a matter property. But of course, in PP or things, it's very difficult to define geometry. So what do we need, to be able to say, aha, I see a clear signature that associated with a bulk matter, that to be able to associate with something that I can describe the geometrical shape of this matter.
Right. So yeah, I think this is a very good point. Right. I think we can go back to in the PP system, that probably is for many people still maybe hard to accept that we have created a QGP medium in PP. One of the reasons is, as you mentioned, it's very hard to think about initial geometry or the initial size of system in PP collisions in an intuitive way, I would say. I wouldn't say it's impossible, but maybe it's not as easy to think about as in the more macroscopic object that we are more familiar with. We are certainly push the envelope to the boundary, and this very small system is the shape and the size is not so easy to think about anymore. But I don't think that's the reason to but it's not the reason that we would reject the idea that there's a similar.
I mean, I don't reject it. Idea,
I
just want to know, what would be kind of ambiguous that to be able to say that this, because the way I look at the like you can get a V2 from, say, two particle correlations or that kind of things. So if I, no, the way I see it is that if there is a true hydrodynamic V2, then of course using two particle correlations, you can get the V2 using two particle correlations. Okay, but the reverse is not necessarily true, because you could have some parton-parton interaction to some extent, some level of interactions that you have a two particle correlations. Okay, then you use the, this model, basically V2 to fit those things. You will be able to fit, but but it's not necessarily that's the unambiguous picture behind those things. So that part I'm a little bit, because especially at least I don't view PCI as has a hydrodynamical behavior in PCI itself per se, but even I don't know how the PCI, whether PCI implement some kind of parton-parton interaction some level, but it could be something in the the fragmentation or something. I don't know. But why it has a good description on those VN behaviors is not clear to me.
Oh, but the PCI doesn't give us the feature in the data, right? Yeah. I think this long range near side ridge is the, as I mentioned earlier, is the smoking gun feature that PCI doesn't give us. So that I don't think PCI has the signature seen in the data.
But the other comparison you had was, why somehow the dashed curve goes through the data so much. But it's just
what I mean is that, right.
Yeah, something like that.
Can you still hear me?
Yeah, I can hear you.
Okay, right. I think what I'm implying here is at low multiplicity, these V2 are dominated by non-collective correlations. So that's why the PCR describes the data very well. So those doesn't involve partonic rescatterings, and you just short-range correlations, or what we call non-flow correlations. And as you go to high multiplicity, these non-flow correlations will gradually get suppressed. And at some point, say around 80, then there's something new starts to emerge in the data, but not in the PCI. So that's why there's the enhancement. The enhancement is very important. So in this region, a low multiplicity is the physics seems to be well understood using PCI, but at high, there's something missing in PCI at high multiplicity.
But even for those, what you call, I would call intermediate, say multiplicity, say 60 or 50. Even if you use multi-particle correlations, you will still see those behavior, right?
That's not clear. We haven't done that in the JS yet.
Okay.
So that's next. That's it's certainly is too early to claim. That's why I always put a question mark, right? We see some indications, just like when we first published the ridge in PP, we were very careful in how we interpret that. There is some indication that there is the effect we see is reminiscent of what has been seen in earlier in AA collisions, in PP collisions. But of course, there are many subsequent studies too, including the multi-particle study. I think we should do also the PID study. Yeah, so only then all those we can draw the conclusion one way or the other.
Okay, no, I agree. No, that's Good point. I appreciate that. Thank you.
But I think in terms of just one remark, in terms of what's missing in the model, in all the fragmentation model where people do the parton showers. So there's no model ever implement rescatterings among the showers produced, and so the one always call the quotation mark around QGP, because to generate V2 you don't need a thermalized QGP medium. You need partonic rescattering with some initial space coordinate anisotropy. So that's all you need. So maybe when the simplest way one can do it, maybe take PCR or other fermentation model and try to implement rescattering among showers. It may already generate some effects.
Okay, maybe one last question, quick question from Hemi. Yeah, please.
Okay, thanks. Thank you very much for a nice talk, Wei. So you showed in your talk, you showed quite some significant signals. For example, the near side ridge and anisotropic flow that supports QGP signal in small system like in PPPA or even in plus minus collisions, and even in a single high energy parton fermentation in vacuum. So that's nice. But what about quenching? I mean, if there is a QGP for formation in a small system, there must be, I guess, there must be some energy loss mechanism going on, right? So do you guys also observe some jet quenching or heavy quark energy loss phenomena in small systems, or?
So, like, for example, in PP or PLED, or you are talking about a single jet. Well, okay, maybe. Well, for example, in PLED, right? In PLED, I think there people always say that there's a puzzle that we don't see jet quenching in PLED or PP. Well, in fact, if the evidence is that we don't see a suppression in our PP in PA. So it's one. So in fact, that's perfectly expected, because if you think about the size of the system, the reason we see clear suppression of the high momentum particles in AA collisions, so that's because of the system size is very important. So you will be able to have a couple of scatterings when the parton goes through the medium, and when you shrink to a very small system, the probability for the high momentum particles to lose energy going through a small system is much lower. Therefore, I don't think it's a surprise that we see almost no effect in RPLED. So there's no positive evidence. Doesn't mean that that it doesn't happen, and is consistent with the expectation. And moreover, I do think there are clear evidence that the hard probe interact with medium in a small system. For example, we see very strong V2 for the heavy quarks, for D0, for drip side, and not yet for the beauty yet. The beauty is very heavy, but that's also consistent with expectation. For PP, we don't. The hard process measurement in PP is even harder. So far I think the measurement still to be improved. Yeah, I don't know if it answers your question. Okay. I think we do have, we do have indications, but in terms of the suppression of the high PT hadron in RPA observable, we don't see a clear suppression, but I claim that is consistent with the expectation in terms of the size of the system.
Okay, so you're saying suppression is not likely to to occur simply because the system is too small, the path length is too limited.
Yes, and we already see that in peripheral AA collisions, the suppression from in RAA is also become very small. So I think it's clearly related to the size of system, and there's no inconsistency with a small system.
Okay. Another thing is, please go back to page 40.
40.
Yes. Yeah. Here you're suggesting the geometrical origin of the anisotropic flow in small systems or in a single high-energy parton fermentation. But and you tried to explain the apparent thermal behavior in E+, E- in terms of this high multiplicity collectivity. But I mean, in E+, E-, for example, in E+, first you have a virtual time-like photon, and this photon is splitted into a quark and anti-quark. Then these heavy quark and anti-heavy quark may be considered as two points, as you're writing here, and can be considered as two hotspots. But in that case, you see that quark and anti-quark, they are moving back to back after they are converted, right, from a photon. So they have no torque between there's no torque between them. So, but here you're saying two hotspots have to interact with each other in order to generate collectivity. So still, I don't see how the collectivity, the apparent thermal behavior in E+- can be interpreted in terms of this picture.
Oh, okay. Let me clarify. So in E+, E-, you create a Q bar, right? And they are almost back to back, as you said.
Yes.
Right.
Yes.
The two hotspots. I didn't mean the two hotspots from this QQ bar. What I mean is that if you look, you want to have a QQ bar, you look at one of the parton. As it enters the vacuum, it can have a earlier splitting into another proton. So you look at one of the two initial parton. So then once it starts to fragment, to split, so it can do early splitting into another proton. It's kind of like a third jet, but very close to one of the parton. And then this, after the initial splitting, then this could be treated as two hotspots, and they are very close, right? They are very close in spatial coordinates, and they may be able to interact with each other and generate the V2.
Okay, I see your point. Thanks.
Yeah, it's not the initial QQ bar.
Okay, thank you very much.
Okay, so your talk is very interesting. So do you mind answer another question from Hongxi?
Oh yeah, I have no constraint, so I can stay here as long as you need. Yeah.
Okay.
So
yeah, thanks.
Hongxi, please.
Yeah, thanks for this nice talk. I just have a very short question. Do you also see the NCQ scaling in JET for this V2?
Yeah, well, that is on our menu next. Yeah, so actually, yeah, what we have done so far is really just the very first step where we see the V2 of the charged hadron. So there's a long list of things we will have to do next, and one of them is to measure the identified particle V2 so that we can see the NCQ scaling. But yeah, we haven't done the identified particle V2 yet. But yeah, but that certainly will be very interesting to look next.
Okay, thank you.
Okay, so it's almost about 2 hours. So again, thanks for your very nice talk. It's very interesting, and looking forward to your new result in future. And also thanks everybody for joining this seminar. Okay, so now let's end this seminar. Thank you again.
Thank you.
Bye.
Bye.
Bye bye.
Bye bye.